Hi everyone, welcome to questions on combined techniques. Now I've broken this up over a few different sections and it all collates together at the end, but just so you've got a clear picture of what's going on, you can pause and go back as much as you need to. So here we've got compound F, it's a trans stereoisomer. So again, highlighting things, this is going to come in handy later on. And then we've got a bunch of other information to help us out. So we've got the percentage composition by mass, and then also we have the infrared spectrum as well. We've then got the mass spec of it, so we have that information there. And here we have, this is where it's all together. So now if you need to go back and pause so you can see the spectra a little bit easier, then by all means do so. That's absolutely fine. So what we need to do is we need to determine the structure of F and then explain all you're working out for it, 6 marks. So starting off with the percentage composition by mass, that's where people always start with that. Everyone pretty much picks up the marks for those. So let's try and work out a bit of empirical formula if we can. So we're going to take our percentages, which we have at the very top there or previously, if you're going to go back, and we're going to divide it by the mass numbers. So carbon's 12, hydrogen's 1, oxygen's 16. And when we get those values, the 5.72, the 8.6, and the 1.425, we're going to divide by the smallest of those numbers. So that would be the 1.425. Divide by that, we then find out we have 4 for carbon, 6 for hydrogen, 1 for oxygen. So that we have is our empirical formula. Now, we then need to look at this other information that we have. Now, if we look at that there, it's got the red star above it. That is our molecular iron peak, our M+ peak. And if we look at that, we can see that it is at 70. So these here are pretty much the workings that you need to show as well in its entirety. So we've got that, molecular iron peak is at 70. So we know that the molar mass, therefore, is going to be 70 grams per mole. So we can then just double check that the empirical formula that we worked out is what it needs to be. So potentially, it could be perhaps, it was say 140, we've got to double everything up perhaps. But we work out the MR of our empirical formula, we find it's 70, so we know that the formula, the empirical, is the same as the molecular formula, which is C4H6O. And that's what we're dealing with. So far, so good. Now, let's go to our infrared. We have a peak, a sharp peak, looking like that there. Again, this should be looking familiar. We know what this peak is, hopefully. So around that range there, 1630 to about 1820-ish. Again, you'll be given this information in your data sheet. That is a carbonyl, that's a C double bond O. And that's all there is to it. And people normally tend to look and think, okay, where's the OH in this? But just as it happens on this one, there isn't. So we don't have a nice broad peak around the 3000. So we just have that carbonyl there. That's all we can get from it. Now, we then need to look at some functional groups and try to work out a little bit of a structure to this. Now, if we go back, that's one thing I highlighted at the very start, was that it said this compound F was a trans stereoisomer. So therefore that means there must be a carbon-carbon double bond in there. Now, difficult to sort of pick out from the infrared spectrum, perhaps, but that's why it's told you in the question that it's a trans stereoisomer. Now, if you don't know what that is, then you don't know that it actually has a carbon-carbon double bond in there. So that's something we can determine from that bit of the question that we've been told. Now, if we look at that peak there, it's got the star above it. Now, it says in the question, in the mass spectrum, the peak with the greatest relative intensity, the one that's got the star in it there, that second star, left-hand side, is caused by the loss of a functional group from the molecular ion of compound F. Okay, so we've got to think, right, what could that potentially be? So because it's at 41, we've got to think, right, well, what could it be perhaps? What can we lose that gives us a peak at 41? And so what this actually is, and we know also we have a carbon double bond to an oxygen. So if we were to lose, say, an aldehyde group, or perhaps it's due to something else. This is where you've got to have a little bit of piecing things together now. You think, okay, what could 41 potentially be? So what could we lose to then result in that peak there? So we're going to lose a functional group to then leave us with 41. So what that 41 is, if you're then just thinking it's carbons and hydrogens, it'd be C3H5 plus. Obviously that needs to have that plus charge on there. So that's what the peak at 41 is responsible for, is the C3H5. If you do 3 carbons with 5 hydrogens, you find it makes 41. So you think, okay, we have that. The only reason we got to that is because we lost an aldehyde group. So we know we're starting at 70, thinking, okay, how do we get to 41? Work out the difference. Well, what could that potentially be functional group-wise? It could be a C, H, and an O, an aldehyde group. That's why we're using the mass spec along with the molar mass, trying to work out, again, trying to piece this all together, trying to find out what this actual structure is of compound F. So once we've done that, we should be in a position where we can actually try and put this structure together. So we know we've got a carbon-carbon double bond in there. We know we've got an aldehyde in there somewhere. Again, that links to the carbon double bond oxygen that we have. So hopefully we can try and put something together that looks like that. That is the end game. That is the final bit there. So people can tend to do pretty well with that. They like the empirical formula. They can identify a carbonyl group from infrared. They can spot the M plus peak and then make sure that their empirical formula is also the molecular formula. And then working out the particular ions, so the little pieces of the molecule that give those relative intensities, people can do that. And then you've then got to put it all together. And it's just a bit of practice trying to piece everything together and then give yourself a final structure, which should be looking something like that at the end. So we've got our carbon-carbon double bond in there. We then also got our aldehyde group in there as well. And so that C3H5 would be, like, say, everything else but that aldehyde group there. So hopefully we're trying to get, obviously, hopefully getting as close to 6 marks as possible. So hopefully you manage to get somewhere near that. But that is obviously bringing all the skills that you need together into one question. These questions come up quite a lot as well, because it pulls in all the skills that you need on all your analysis to try and get to a final product or final structure. Okay, so that will do us for today with some combined techniques. See you next time.